The single most important skill students learn from Bootstrap is called the design recipe. This video talks about how the recipe is used by students and will walk you through several examples. The second video will introduce how the design recipe is used by teachers to answer student questions and diagnose common student challenges. Perhaps the best known example of a word problem is the train leaves Chicago problem. Now, setting up the equation to model what's going on is really hard, but solving it is relatively easy. Word problems sit at the nexus of many algebraic concepts. Students have to read the problem, identify what information is given, relevant, and changeable, and then model the system described in the word problem using a functional expression. Now, there are several best practices that math teachers have used for decades to help students with word problems. State the problem in your own words. Circle what's given, what's changeable, and what must be returned. Show your work, right? We ask kids to work through a few examples. Write the function, and then, of course, test it out using your examples. Now, all of these practices form the core of Bootstrap, which introduces a powerful technique for solving word problems called the design recipe. The steps of the design recipe are introduced at the end of Unit 3, and no new material is added for Units 4 and 5. They're 100% devoted to having students practice the design recipe with simple functions. So, the recipe formalizes these best practices into 3 broad steps. Write the contract and purpose statement, write 2 examples and circle what changes between them, and then finally, define the function. Now, it's useful to think of these stages as 3 links in a chain, with students translating the word problem from each link to the next. Each translation refines the problem more and more, until what's left is the formal function definition. Each translation depends on the step before, so it's essential for teachers to explicitly connect each step to the previous one. Now, by placing the emphasis on the series of steps, Bootstrap builds confidence for students by having them trust the method. They think, well, I might not know how to get the answer right away, but I know that if I can complete one step, I'll be able to get to the one after it, and after that, and so on. So let's walk through 2 examples from the curriculum and talk about how the design recipe is used with each of them. First problem. Write a function gt, which takes in a number and produces a solid green triangle of the given size. Step 1, contract and purpose. The contract and purpose statement are a formal way of asking students to write the problem in their own words. The contract specifies the name, domain, and range of the function, and students should be really comfortable with contracts at this point in the course. By reading the problem, we know that the function should be named gt, and that the only thing in its domain is a number. It can be helpful to have students act out the problem here, so they really understand that the function is always making a solid green triangle. The only thing it doesn't know is the size. Finally, we know that the function produces images, because all triangles are images. Now, the purpose statement is not introduced in Unit 3, but from Unit 4 onwards, students will always be given the space to write the problem in their own words. For this one, a good purpose statement might be, given the size, make a green triangle of that size that's solid. So step 2. Examples should always be derived directly from the contract and purpose, not from the original word problem. If it turns out that students need to go back to the word problem, it's a good sign that they probably missed something in their contract and purpose. So for this function, the contract tells us the name is gt, and that we have to provide a single number as input. We can choose any number we want, so I'll just pick 18 for this example. Just based on these 2 pieces of information, we know that the example should start with gt of 18. Using the range in the purpose statement, we know that we need to draw a solid green triangle of size 18. The second example is also generated from the contract and purpose, this time using a different number, let's say 42. And it's easy to notice that everything in these examples is very similar. The only thing that changes is the number. But what does that number mean? Is it the number of triangles on the screen? No, that's the size of the triangle. So we'll circle the numbers 18 and 42 and label them with size. Step 3. Once we have the examples written and labeled, it's easy to go directly to a finished definition. As before, we want to make sure that everything we're writing here comes from the previous step, the examples. So everything in our definition should be copied almost verbatim. If we come to something that's circled in our 2 examples, instead of copying that, we're going to copy the label instead. Both examples use the same function name, gt, so we'll copy that. They use 2 different numbers as inputs, so we have to use the label, in this case size. And for the body of the function, we're going to copy the triangle, solid, and green from the examples, since it's the same for both. But again, instead of copying the number, we're going to copy the label size, because the number is changeable. When a student clicks Run, the computer will actually test the examples out to make sure the function satisfies them. If it doesn't, the computer will warn the student and let them know which example went awry. This is a terrific way to teach students the benefits of showing their work, since now they get an immediate benefit. The computer literally checks the code for them. It also goes a long way towards reinforcing the idea that these different representations are connected. Let's do another example, this one using a more traditional math problem. A car is moving at 65 miles an hour. Write a function that describes the distance the car has traveled as a function of how many hours it's been moving. Step 1, contract and purpose. As before, we need to identify the name, domain, and range for this function, and then rephrase the problem in our own words for the purpose statement. Step 2, write 2 examples, being sure that everything comes directly from the contract and purpose statement, not from the original word problem. Then we circle and label the parts that are changeable. In this case, what do the numbers 2 and 9 represent? Are they the number of miles that have been driven, the hours that have been passed, the passengers in the car? This is a crucial step that many students skip, so be sure to draw attention to it. In this problem, those numbers represent the number of hours the car has been moving. So we're going to label those circles with hours. Step 3, using only the information in the examples section, derive the function by copying everything that stays the same and using labels instead of the parts that are changeable. The design recipe is a powerful tool for students, since it asks them to think through an unstructured word problem in a structured way. Not only is it helpful for solving programming problems, but it can be used to set up the formula for nearly any word problem in a traditional math class. It's also important to note that each one of the steps represents a different representation of the function. The contract is merely a mapping between domain and range. The examples are a table of discrete inputs and outputs, and the definition is a symbolic formula. Finally, the design recipe is a powerful tool for teachers, since it forces students to make their thinking explicit at each stage. Instead of looking at a wrong answer and trying to figure out where the student got lost, the design recipe allows us to see their thinking as it develops. You'll want to make sure that students complete the design recipe worksheet before they move to the computer. From this point forward, every single problem students face in Bootstrap is phrased as a word problem. Bootstrap word problems require that students answer them using the design recipe, and you can choose to use the same recipe for regular math problems. This will ensure that students see the connection between what they're doing in their games and what they're doing in math class.